Bien, je vais faire une introduction en français, mais après, Thierry parlera anglais. C'est un très grand plaisir d'avoir Thierry avec nous aujourd'hui. J'ai envie de dire de nouveau, puisqu'il est déjà venu ici, mais il est toujours le bienvenu. Voilà, alors je vais présenter Thierry en 2 mots, mais même si presque tout le monde ici le connaît. Donc Thierry, c'est un grand spécialiste de la physique de basse dimension et du désordre. Il dit lui-même que s'il est spécialiste de désordre, c'est parce qu'il est très désordonné. Moi, j'en crois pas un mot, parce que ces articles, ces séminaires sont toujours parfaitement clairs, ordonnés, logiques. Donc je crois que ce désordre intrinsèque du personnage est une légende. Alors, Thierry, en 2 mots sur sa carrière. Tu as fait ta thèse en 87, c'est ça?
C'est ça.
Alors, sous la direction de... C'est avec Heinz Schulz, mais on voit dans les papiers officiels que c'était Friedel, ton directeur de thèse.
Oui, parce que comme il y a eu la nouvelle thèse, Heinz est passé du jour au lendemain de directeur de thèse à non-habilité, donc ne pouvant plus diriger la nouvelle thèse.
Ah, d'accord.
Voilà.
C'est Friedel.
Et donc Friedel a signé les papiers, mais c'est bien Heinz qui était le directeur de thèse.
Oui, voilà ça. Il est rentré au CNRS immédiatement, ou peut-être la même année, ou peut-être même avant, je ne sais pas. Enfin,
officiellement en 86, effectivement.
Oui, c'est ça, voilà. Donc,
mais c'était l'année où le Conseil constitutionnel a annulé les élections des commissions CNRS. Oui. Donc en fait, ça s'est fait en pratique en 87.
En 87, voilà. Voilà, donc il est rentré au CNRS en 87 pour quelque chose comme une quinzaine d'années. Pendant ces 15 ans, tu as passé 2 ou 3 ans au Bell Labs, ouais, quand même. Et puis en 2002, il a quitté la France, et en particulier Orsay, pour aller s'installer à Genève, où il est toujours, voilà, professeur ordinaire mais extraordinaire, à Genève. Voilà, donc on ne l'a pas complètement perdu, puisqu'il a été élu à l'Académie des sciences il y a une dizaine d'années maintenant, 12 ans. Donc, comme j'ai dit, c'est un spécialiste de la physique de basse dimension, physique 1D et 2D. Son livre sur la physique 1D, c'est la Bible de ceux qui s'intéressent à la physique quantique à une dimension. Je crois qu'il n'y a pas de concurrence, à ma connaissance.
Oui, il y a un très bon livre de Zwick, Nersessian et Gogolin.
Voilà, mais quand même, ça reste la Bible. Voilà. Donc, sa recherche, c'est une combinaison donc, des aspects de physique du désordre, avec la question d'Anderson, des interactions, avec des plateformes qui sont très diverses. Ça peut être les supraconducteurs organiques, ça peut être les chaînes magnétiques, un peu comme celle qu'on a vue ici, mais version quantique. Et puis ça peut être les atomes froids. Thierry est un théoricien très recherché par toutes les équipes expérimentales qui s'intéressent au système de basse dimension. Voilà, donc il s'intéresse aussi au problème des féoles quantiques, et c'est de ça qu'il va nous parler aujourd'hui, donc en parlant des féoles dans des systèmes quasi 1D, en interaction.
Merci beaucoup, Jean. Moi aussi, je vais commencer en français et passer en anglais. Donc d'abord, c'est un grand plaisir, effectivement, d'être là. Et je remercie évidemment Jean pour cette invitation et aussi pour l'introduction qui me fait rougir intérieurement. Et je suis ravi de pouvoir vous parler un petit peu des recherches qu'on a fait sur les féoles. Et je pense que je vais basculer en anglais. I'll switch to English for the research part. So I'll say again that I would like to thank Jean very much for this invitation and the kind introduction that he did. I'm going to tell you, and we will do a 4-hand piece together with Leo Falani, who is here because he's the guy who did the experiment. So I'll just flash, in case some of you cannot be here for his presentation, some of the experimental results. But this afternoon, Leo will do a full presentation of the experiment. So every difficult experimental question should be directed to him. And the opposite, absolutely. Voilà. So I'm going to tell you about some obsession that we have had for a long time. You will see about Hall effect. I'm not sure I will tell much about topology. Actually, I will avoid topology, but that's an important question. So as Jean was saying, I'm in the Department of Quantum Matter Physics at the University of Geneva, and this is the funding organism that made this research possible. I have also the great pleasure to be the director of a network on materials with novel electronic properties which is an association regrouping various universities working on quantum materials. If you want to know more, I encourage you to go to see the website, which is w3manep.ch for Switzerland. So first, before I go to the talk itself, this is a talk which has been done, as I said, we had a great chance to have a collaboration with Leo's group, and the person who was heads-on the experiment was Tianwei Zhu, and of course all the group of Leo. And on the theory side, there are several aspects of this work. So this is something which was done in collaboration with many, many people. I want to especially outline Michele Filippone, who was the driving force behind essentially the entire project. He's now in CEA in Grenoble. And a very, very talented postdoc at the time in the group, Sebastian Grechner. We had, and Charles Bardin, sorry. And we had a fantastic collaboration with a group of Uli Scholvöck, it will be clear during the talk. And more recently, and especially in collaboration with experimental aspects, we had the great pleasure to have a collaboration with Cécile Repellin, who is also in Grenoble. And then there are some more analytical, so this is more on the numerical side, I would say. And we had some advance recently on the analytical side with Edmond Rignac and Roberta Citro. And if I have time, hopefully, I will tell you about some recent work that we did in collaboration with Katalin Alati, who is an incredibly talented postdoc in my group, on triangular ladders. So let me, without further ado, go into novel physics, which is something which was done in 1879. Now, I could not remove this. I was at a conference where we were supposed to talk about long-standing problems. So it's hard to beat if you want something more long-standing than this, which is the Hall effect. So you all know the Hall effect. So let me still remind briefly. You take a piece of metal, you pass a current along a direction, let me call it X, and you have a magnetic field, so there is a Lorentz force. The Lorentz force deviates the electrons, they accumulate on one side and deplete on the other side, so this creates an electric field which equilibrates the Lorentz force. And then if you take this semi-classical vision, or if you take a non-interacting vision, you find that the whole voltage here, divided by the longitudinal current and divided by the magnetic field, is supposed to be 1 over the number of carriers. And that's what makes the Hall effect very useful in condensed matter. Note that I'm not talking about quantized Hall effects or fractional quantized Hall effect, which would occur at extremely strong magnetic fields. Here I'm talking about the stupid Hall effect, which is the small field limit. B is very, very small. Just to give energies, 1 Tesla is 1 Kelvin. Fermi energy in solids is 10,000 Kelvin. So you usually apply fields which are much, much lower than 1 Tesla. So you're really at the limit of very, very small field, unless you work very hard to increase the field and lower the Fermi energy, which is the condition at which you can observe a quantized Hall effect. But the idea is that the Hall effect is supposed to measure the inverse of number of carriers, and therefore it's very useful in principle to tell you how many carriers you have in a band. And this is an urban legend. Mostly, this formula is always wrong. Why? We know without interaction that the Hall effect measures actually the curvature of the Fermi surface. So this 1 over n works when you have a spherical Fermi surface, k squared over 2m dispersion. But as soon as you have a more complicated band, this is completely wrong. And of course, then the question is, what does the Hall effect measure? And there are ways to relate it to, as I said, integrals of curvature of Fermi surface. And there are beautiful formulas. In particular, there is one which is called the Thouless-Komoto formula, which was part of the reason why Thouless got his Nobel Prize, and you can relate it to topological invariance and so on and so forth, but this topological invariance depends on the Fermi surface. So this is practically never correct in practice if you look at realistic solids which are not semiconductors with essentially a spherical Fermi surface. And then it becomes even worse when you put interactions. This is a totally open question. So if I'm thinking about what the Hall effect measures in a system with interactions, nobody knows the answer. There is blood on the walls of conference on high TC, for example, where people, because there are measurements of Hall effects in strongly correlated materials, but to interpret these measurements is, of course, an extremely complicated situation. And with interactions, the limit in which people could solve is when the magnetic field became very, very large, in which case you create gaps in the system because of the Landau levels. And then there is the beautiful both theory and experiments on the integer and especially the fractional quantum Hall effect. And Nathan is a person who pushed this into cold atoms. But there you're protected by the huge gap which is coming from the very large magnetic field. In this talk, I will mention large and small magnetic field, but mostly keep in mind that I'm interested in the small field limit, just for this. So it becomes even worse if you try to consider materials which have a low dimensionality. Why? Because low dimensionality favors interactions. In particular, Jean was mentioning one-dimensional systems. If you're in a one-dimensional system, interactions play a very central role, lead you to a physics which is very different from the Fermi liquid physics in high dimension. Fermi liquid means essentially you can ignore the interactions in a system. Well, it's not true in one dimension. If you ever queued for a cafeteria or a movie, you know that if you push the person in front, the person pushes the person in front who pushes the person in front. So even any interaction will change drastically anything into a collective excitation. So this is very, very drastic change of the physics. So the question is, what would be the Hall effect of a system made of many weakly coupled chains by tunneling? And here I wrote an energy or an Hamiltonian. So this is the kinetic energy of the system, of the chains. This is the first line. This is the interaction that would exist in every chain. If I just take these two terms, I would get what is known as a Tomonaga-Luttinger liquid, which is something which has been studied in its own right, and which has physics, as I said, very different from Fermi liquids. And then I put the tunneling between the chains. Let's say T perp is very small compared to VF, or T parallel, if you prefer. So I have weakly coupled chains here. I put the gauge field, which corresponds to the magnetic field. And what I want to do is to pass a current along the chains and measure the voltage which is in the direction perpendicular to the chain. Now, most of the people who would do 1D system would simply not write this second term here. Usually it's completely ignored, because this second term corresponds to the curvature of the dispersion relation around the Fermi point. So usually you can linearize the dispersion relation around the Fermi point. By the way, in higher dimension, this corresponds to making an approximation that the density of states is a constant. So it's not, you know, a crazy approximation. Unfortunately, when you do this for the Hall effect, the theory becomes intrinsically particle-Hall symmetric, and then you find immediately that the Hall effect is zero. The small field Hall effect is zero. So this is an artifact. This doesn't correspond to the realistic material, but it complicates your life because you have also to include these curvature terms in the dispersion relation, which means you have difficulties using the standard weapon weapons of Tomonaga-Luttinger liquids, and this makes the theory very complicated. You can compute the Hall effect using linear response, using Kubo formula. I mean, it has an expression which is relatively simple in terms of the conductivities. But of course, computing practically these objects is very difficult. Let me give you the answer for the weakly coupled chains that I showed without interactions, because there we can do the analytic calculation. And you see immediately that the Hall effect, which is essentially the Hall resistance here, is proportional to the field. Okay, is inversely proportional to the density, but there are other factors like the curvature term. You see immediately it's proportional to the curvature. This is not 1 over n. This depends on the form of the dispersion relation. Computing for the model I gave you is very difficult. I'll come back to this in one moment, because you can only do perturbation in T-perp. You have to do the expansion in B if you want the small field regime. The curvature is a pain in the neck, so you usually expand in the curvature. All this makes the calculation very complicated. So when calculations are complicated, you turn to experiments. At least if you know the answer, it's more easy to know which approximation to make to find back the answer. So this helps. So here are experiments that were done on organic conductors and superconductors, which are so-called Bechgard salts, because they were synthesized by Klaus Bechgard. These are stacks of molecules with very anisotropic hopping. Along the direction of the stacks, the T parallel is about 3,000 Kelvin, or the bandwidth is around 3,000 Kelvin. In the perpendicular direction, the hopping is only 100 Kelvin, so there is a factor of, let's say, about 20 between the two directions. And if you go in the third direction, it's again a factor of 10, it's again 20 Kelvin. So let's say 3,000, 200, 20. So this is a very good approximation or a very good experiment for the kind of models of coupled chains that I showed you. So this is exactly this. You pass a current along the chain, so the stack of molecule, and then you measure the voltage in one of the direction perpendicular to this. So this is an experiment done in Orsay in the group of Denis Jérôme. Note the date, it's 25 years ago now. And you see a very strong temperature dependence of the Hall effect between 300 and about 100 Kelvin, which is the temperature at which the tunneling between the chains become really coherent, and you should consider that this is really a two-dimensional plane. This system have what is known as dimensional crossover, in the sense they are really quasi-1D in this range of temperature, and really 2D and then 3D as you lower the temperature. The question of dimensional crossover would deserve a seminar in itself. So here, just trust me, the quasi-1D regime is above 100K. So great, we have something anomalous. We have a strong temperature dependence of the Hall effect in this regime. Now, this is an experiment done in the group of Laszlo Forró in Lausanne, who is also someone who knows perfectly well how to measure transport. And you see the result is completely different. The temperature dependence of the Hall effect is essentially flat. So the experimentalists themselves do not agree on the answer. And since then, nobody was brave enough to do a third experiment to say which one of the two is wrong, if any, or maybe they are both right, but theoretically they should give the same result. So maybe there is an ingredient we have forgotten, but nobody at that stage, as far as I know, understands the discrepancy between these two experiments, not to mention to know what is the right answer for the whole temperature dependence of the Hall voltage. We have a study, a theoretical study done with Gladys Léon and Christophe Berthaud, which predicts a power law in the quasi-1D regime with an exponent which depends on the interactions, let's say, on the so-called Tomonaga-Luttinger liquid parameter. So, of course, we would be more pleased if this experiment is correct, but since we don't know the answer, we are still trying to decide whether this theory is correct. It's a theory which uses a formalism which is known as memory matrix formalism or Morris-Svensic formalism. It's uncontrolled, but is supposed to give pretty good results. So I hope that this answer is correct, but in the absence of either experimental confirmation or information, I cannot really tell you. So for this reason, we decided to turn to other geometries and to look at things on which we could do more controlled calculations. And one geometry begs to be studied, and it's ladders. So I will, instead of looking at many coupled chains together, we will start, small and say, let's look at 2 chains, 3 chains, 4 chains, 5 chains, and okay, if I go to n, go very large, I go back to the 2D plane, but let's start first by having very few chains coupled together. If you want, it's the smallest 2D system in the world, and hopefully by increasing the number of chains, we can understand something. And already the question is, what would be the Hall effect in a system made of 2 chains? Because you can do exactly the same thing, pass a current along the chain. If you put a gauge field here in the tunneling, there will be a Lorentz force, which will deviate particles to the top chain, deplete the bottom chain. So you can measure the imbalance in population between the top chain and the bottom chain, and therefore you can measure the Hall effect on such systems. Because this is finite in transverse size, you even have perfectly the boundaries. And so you can measure. So there are 2 quantities, and I will try to be careful not to mix them. There is the Hall imbalance, which is the difference of population between the top chain and the bottom chain. And there is the Hall voltage, which is the difference in chemical potential between the top chain and the bottom chain, so that there is no imbalance. And in solids, this is realized because when you have an imbalance, you generate an electric field which equilibrates the Lorentz force. Here, you want to equilibrate the Lorentz force by making it more difficult to go to the top chain. And these 2 quantities are related but different. I can measure simply N2 minus N1. This is the Hall imbalance. And I can apply a chemical potential between the chains to make sure that I have the same number of particles on both chains, and this difference in chemical potential will be the Hall voltage. Of course, they will depend on the current that I pass on the system, and they will depend on the gauge field, on the magnetic field. Just as a comment, this geometry of ladder was used by people who did exact diagonalizations. You know, when you do exact diagonalization, you can do 4 by 4, essentially. So people try to study 2D systems, but when you do exact diagonalization, you are limited in the transverse direction. And there is a very nice old paper by Carlos Balseiro, in particular, where they try to analyze the Hall effect in these systems. Okay. So now I want to compute the Hall effect. So theorists will do this. Theorists will do a periodic boundary condition on the ladder. There is a magnetic monopole, if you want, in the middle, which is producing the magnetic field, which is radial here and will give you the hole between the top and the bottom. And then you put a flux to generate a persistent current, which, because of the boundary condition, will circulate here. That way, you're nicely in equilibrium, and you can compute steady state, the population difference. This is nice, but this is, to the best of my knowledge, and of course, I turn to you, difficult to realize experimentally, both in condensed matter and in cold atoms. In condensed matter, if you deal with bosons, you have Josephson junction arrays, which are a potentially good realization of this. Fermionic ladders are a little bit more difficult to get. So we try to find a practical way to study the Hall effect. And this is what was done with Sebastian Grechner and Michele Filippon, and I'm going to describe it to you. So this is an image view of a three-leg ladder. By the way, the symbols are not random. The size of the dot tells you the population. This is the result of DMRG calculations. So we have the ladder, we have the flux here on each plaquette. So this is exactly the situation. And the arrow, the black arrow, tells you the current, how the current passes. You see that, by the way, it doesn't pass uniformly on the ladder. Much more current passes on the central wire, but we pass a current. So what is the protocol that we want to do? We take the system and we give it a kick. When you give a kick, you start having a current which, as a function of time, will start to build in the system. Of course, in the numerics, we are in a box. In the experiment, probably in a trap, hopefully in a box, but most of the experiments. So get rid of the trap, get rid of the trap, and get rid of the trap. Sorry, that's my obsession. I had to say it. No, so more seriously, in the simulation, DMRG is usually done in a box with hard boundary conditions. I'll come back to that, because otherwise it makes the numerics much, much more difficult. Okay? So this current will go crashing on the walls of the box, be reflected. This is what Jean was saying for his soliton. You don't want the thing to really crash at the edge. So these times are all smaller than the time for this to happen. Now, when the current is building, there is also an imbalance which is building between the top and the bottom because of the Lorentz force. And you see that these two quantities are strongly time dependent. So there we are really far from equilibrium. On the other hand, if you work out the ratio between the two, which is what you want to do if you want to get the Hall effect, you will see that the ratio stabilizes very rapidly with a time scale which is much shorter than what you need before things go crashing on the edge. They stabilize to a constant value. And we can test on non-interacting fermions that this constant value is the right one, is the one that corresponds to the other geometry, the equilibrium geometry. So this is a practical method to compute, because as I said, DMRG doesn't like periodic boundary conditions, but this is also a practical method to realize the measurement of the Hall effect in an experiment, because giving a kick and then measuring this quantity is extremely difficult, but as you will see in the talk of Leo, this is something which is potentially feasible. Just to show you, I'll go very fast on this, to show you a little bit more simulations. This is the simulation for a two-leg ladder of fermions. This is the imbalance here. And this is as a function of the interactions in the system. I forgot what is the value of T-perp. I think it's something like 2Tx. So in that case, T-perp is larger than Tx. And you see that the Hall effect is completely dependent on the interactions. This is for various fillings. It's completely dependent of the interactions. But you see something which is interesting, is that if the interaction exceeds a certain value, suddenly all the curves for all the densities go to one constant value of the imbalance. So this was a surprising result. And it tells you that you recover some form of universality. And now when you plug in this imbalance and you compute the whole voltage, the big surprise is that you recover 1 over n, 1 over the density. So what we had, this is for bosons. So this is M equal to a ladder of bosons. for various value of the interaction, u equal 8 and u equal 16. These are the crosses, the red crosses are u equal 8, and I think the open box are u equal 16. And you see these dotted lines show 1 over n. So you see again, the Hall effect is strongly depending on density, but if you go to small density, you recover the 1 over n behavior. Of course, when you go to 1 boson per site, you go to a Mott insulating state, and the Hall effect becomes 0. This part is fermions, is free fermions, and then you find the 1 over n at small density, but also when the band is nearly full. So we had this big surprise that if the interaction became large enough, the imbalance went to some universal value, and as a result, the whole resistance being the voltage divided by the longitudinal current and normalized to the magnetic field, was giving you back this value that I said is practically never correct, and is certainly not correct as a general value for the geometry we are looking at. You saw that in general, the whole voltage depends on interaction, on the T parallel, on the T perp, and so on and so forth. So this was a big surprise, and this was something we wanted to explore more. So the first exploration was, is this procedure that we do fooling us? So for that, we teamed with the group of Uli Schölwerk, and Max Büser is the person who did the practical calculations, because Uli is a professional of DMRG, and he has a code which can do DMRG with periodic boundary condition, which costs much more computational time and requires to be extremely optimized. So what we did, we compared the kick procedure and the periodic boundary procedure. And to cut a long story short, I will show you data. We get totally identical results on a ring and on a box. And in addition, we showed numerically that there is this practical procedure, and I'm sure Leo will tell you much more on how to do this in the experiment. There is a practical, there are even several procedures. The one used in the experiment is slightly different than the one which was in this paper, to compute the whole voltage, which, as I said, consists in essentially putting a chemical potential difference and to ensure that the imbalance is 0. So just to show you that it works, here is the procedure with a kick. So you see, you have the polarization, you have the current, you do the ratio, converges very nicely to a constant. This is for non-interacting particles. And then here you have the comparison with the periodic boundary conditions and the tilt, which is the kick, if you prefer. And you see that for all fluxes, here the magnetic field is not small at all. It goes from 0 to a flux of pi per plaquette. You see that the tilt and the periodic boundary conditions are giving essentially the same result. You see also that there is a singularity of the whole imbalance at a special value of the flux, and this I will comment on the next slide. Now you can do the whole voltage, and this time this is for interacting particles, and you see again that we get perfect agreement between the two procedures. There is a kink in the whole voltage here at a given value of the flux, but the main message here is that the two procedures agree perfectly. So we can use our procedure for people who do not have the super optimized code. We can do the kick numerically, but more importantly, the kick can be done in experiments. Why look at the whole voltage instead of the whole imbalance? Well, both quantities are interesting, but let me show you the example of a two-leg bosonic ladder with a flux. So this is a problem that actually we studied a long time ago with Edmond Rignac, with at the time, because there were no real cold atom experiments at the time, at least turned towards condensed matter. This is 2001. We had Josephson junction arrays in mind. And the idea was, what becomes of a type 2 superconductors if I have only 2 lines of bosons? So do I have vortices? Do I have an Abrikosov lattice or whatever? And what we found is that actually, depending on the strength of the flux, you have two phases. You have a phase which we call the Meissner phase, where the currents are only along the legs. So this is very much like having a Meissner current, which is trying to screen the magnetic field in the phase below Hc1 in a superconductor. And then if you increase the flux, you go to vortices where current starts circulating not only on the legs, but also on the rungs, and you form vortices that form a lattice whose density grows with the flux. So this was really the equivalent of the Hc1, Hc2 for type 2 superconductor. And by the way, this is something that was tested in cold atoms in the group of Monika Eidelsberger and Emmanuel Bloch a couple of years ago. So let me take this, and this is actually the system that was studied here. So now you can guess what this singularity would be. It's the Meissner to vortex phase transition. So it tells you the Hall effect is sensitive to this. Now, I won't go into detail about the fact that we can compute the Hall effect in the whole flux regime. Again, very good agreement between tilt and periodic boundary condition. We recover the universal value of the Hall voltage when the interactions are strong enough or T perp is getting much larger than Ty. I'll come back to this. But compare here the Hall imbalance with the Hall voltage. The Hall imbalance depends completely on the flux, on the interaction, and whatever. So it's a function, it's a complicated function. Okay, fine. If you look at the Hall voltage, all these curves, which were different for the Hall imbalance, collapse on a single curve. Here they are shifted for clarity, but they collapse on a single curve. So the Hall voltage, even if we don't understand why, is clearly much more universal than the Hall imbalance. So if you want to make contact with condensed matter, of course you need the Hall voltage, because this is what is naturally measured in condensed matter. But it also gives you clearly much more universal answers than what you could expect with a Hall imbalance. So this is showing that this has this interesting, I would say, universal behavior, much more than what the Hall imbalance could. Okay, experiments, I will just go very fast because, as I said, Leo will provide all the details. So first, can one get this kind of thing in cold atoms? Yes, these are fantastic systems to get this, because you can realize synthetic dimensions by using an internal degree of freedom. So this is not a real ladder. This is a single chain, but with an atom which has, for example, 3 internal possibility for its internal degree of freedom. And if you do Raman transition such that every time you do a transition, you can pick up a phase which is engineered so that it looks like the phase of a real magnetic field, well, you can realize the equivalent of a very nice ladder. So this is synthetic gauge field and synthetic dimensions. And cold atoms have proven to be the perfect quantum simulator for this type of physics. Actually, the idea of course, measuring the Hall effect was done way before we did the study of the interacting systems. Here is some curves from Leo Group in 2015. There are similar experiments done in the group of Jan Spielmann in Maryland, where they see particle drifting from one quote side to the other side, and of course with dysprosium, the Rolls-Royce of Sylvain, Nassim Bene, and Jean, were 8, I think, no? You get, you see the particle drifting from one side to the next. But unfortunately, all these experiments were done with very small interaction, as far as I know, and don't hesitate to correct me if you disagree. And so Leo went back to his experiment and cranked up the interactions. This led to this very nice paper. So on the theory side, Michele and Cécile were providing the theoretical analysis. I'll go very fast. You give a kick. You see the kick here on the image. You measure the imbalance between the, let's say, left leg and right leg, which corresponds to these two internal degree of freedom. And lo and behold, I'll just show the final curve. You can plot the ratio of the imbalance with the longitudinal current, normalized with the magnetic field, and look at it as a function of the interaction. And you see that this gives you values which are interaction dependent, but if the interaction becomes large enough, well, it converges to the number which for the imbalance we know corresponds to the 1/n Hall effect. So one can say two things. One, that the experiment confirms this universal value of the Hall effect, or at least of the imbalance here in this experiment. Second, that the quantum simulator is also able to compute the Hall effect for other values of the interactions. And you will notice that the theoretical curves, which are the DMRG done at t = 0, of course, they give the same answer in the universal part. They give what we are sure is the right answer if the experiment was done at t = 0. But we are, at that stage, unable to compute the Hall effect at finite temperature, far from the universal regime. It would entail to do the DMRG at finite temperature, which is, of course, perfectly possible, but again, for practical reasons, very difficult. So I think that's one case where I can say that the quantum simulator, at least momentarily, has advantage compared to the laptop simulator, because for practical reason, working, hello Laetitia, the DMRG is reasonably easy to do at t = 0, considerably more difficult to do at finite temperature, and we would need to invest considerable resources to see if we can get a curve which would go in this point of relatively small interaction through the experimental point. Okay, here the goal was to check the universal value, so we didn't worry about it, but this is a challenge. We tried to cook up some approximate mean field approximation, but as expected in 1D, mean field approximations are not very good, and they are not very good. So, okay. Again, everything converges nicely in the universal regime. There is a second set of experiments, again, I won't go in detail, where Leo's group put the imbalance in chemical potential. So in these experiments, they can directly measure the whole voltage, not the whole imbalance. And lo and behold, if you plot the whole voltage, again, normalized to the currents and whatever, so this is the inverse, as a function of n, the curve is very, very compatible with the 1/n result. There are no adjustable parameters here to fit the theory and experiments. So I won't say more on the experiment. This afternoon, Leo will go in great details on the experimental side. So don't hesitate to listen to his talk. And if you cannot be there, well, you have the reference. You can look at the papers. I would like in the, 15 minutes that I have left or something like this, 10. So go a little bit into an analytical derivation of these effects. Because at that stage, this is a numerical evidence. We just did the kick. We got the evidence that we converge to this universal value, but there is neither explanation nor it's numerical experiment versus, I would say, real experiment. or quantum simulation. Of course, we can do calculations for non-interacting fermions, but this is a little bit limited. So recently, together with Edmond Rignac and Roberta Citro, we went back to the bosonized formula, so to the description of 1D system in terms of collective coordinates. So here is an image of the system. To get the whole voltage, we apply this chemical potential difference, which is why the ladder is tilted in one image, let's say, and flat in the other. So we have our two-leg ladder with a flux, and we can put a voltage on one side to compensate for the thing. So the idea is that in 1D, it's convenient to re-express the single particle operators in terms of collective variables, which is for bosons something which has been beautifully done in a paper by Duncan Haldane. I think you will recognize some of the formulas compared to what Jean has used in his course. This works in 1D even if the particles are strongly interacting. So you can push it to way beyond the Gross-Pitaevsky regime. And you get two phases. One is the superfluid phase, which is here. And another is a phase which is associated to the density. Beware, it's not exactly the same than Jean used in his course. It's more that you will represent the density by a gradient of this phase plus higher order terms that I didn't write here. So when you use this representation, you can do this for one chain, you can do this for the second chain. You get the tunneling between the chains, which will give you this kind of terms, because you see exponential of I theta 1 minus I theta 2. And the miracle is that the interacting two systems have a quadratic Hamiltonian in terms of these two phases. And of course, if you get a chain 1 and chain 2, you can also work out the symmetric and anti-symmetric combination. But there is something to spoil the fun, which is that I could do this if I had only the quadratic part here. Then I could go to theta symmetric and theta anti-symmetric by doing the plus and minus combination. But remember, if I want the whole effect, I have to add the curvature terms. And the curvature terms gives you cubic term in the Hamiltonian. So they spoil this nice solution that you could have of this problem. So for models, well-known models like the Lieb-Liniger model and so on, which is bosons in the continuum, these curvature terms have been computed, and they can be expressed in terms of derivative with respect to the density of something called the Luttinger liquid parameters, which are parameters depending on the interactions that exist in the chains. It's not important, the expressions. What is important is this structure, the quadratic part plus this cosine, and then these terms that spoil the fun. So these terms blocked the solution for a long time. So what we realized is that we could try to do an expansion in the curvature. And when you do an expansion in the curvature, you see here the coefficient of the curvature gamma, which appears for at least two chains. You get a little simplification which occurs, which is that you get some correlation function of the anti-symmetric sector, which now you can compute with the system without curvature. And you get an horrible term, which you don't know how to compute, but which turns out to be the average of the current. So you don't need to compute it because you're going to divide this by the current. And so this little decoupling makes the fact that now we are able to practically compute this term. So let me skip the polarization and go directly to the whole voltage, because there we find something which is quite surprising. So we took the whole voltage, we inject, we do things. You notice the current is appearing. We divide the voltage by the current. We divide the voltage by the magnetic field if the field is small. And then we find a relation which is quite remarkable, because what he says is that the whole resistance, which is the voltage divided by the longitudinal current divided by the magnetic field, this is the standard name that people give to this quantity, is equal to the derivative with respect to the density of the log of a quantity here, USKS. And USKS is what people call cone stiffness. This is the weight of the Drude peak of the system without magnetic field. And this is the response of the system to a flux. So this is what determines what people call the persistent current. And this tells if I put a flux on my system, there will be a current proportional to the flux that will flow, and the proportionality constant is this product. So you find a relation between two quantities. One is the Hall effect, and the other is the persistent current, which is a thermodynamic quantity, which describes a system in equilibrium, and which is also, again, as shown by Walter Kohn, the weight of the Drude peak in a transport experiment. So this relation between these two quantities is quite unexpected. Remember that we only proved it in the paper to first order in the band curvature. But we can easily check that this relation is exact for some particular models. And I had in particular an exchange of email with my very good friend Assa Auerbach. Unfortunately, we passed away very recently, where he said that in some rotator model, they also obtained a relation that was like this. But just look at what you get if you have a Galilean invariant system. If you have a Galilean invariant system, then the weight of the Drude peak is all the particles, so it's ρ0 divided by the mass. And when you will do the derivative of the log of ρ0 with respect to ρ0, you find 1 over ρ0, so you recover the 1 over n that I was mentioning before. So for Galilean system, we recover the 1 over n, and we know we should recover the 1 over n for the whole resistance. But this formula gives you more. If you are near, for example, a Mott transition, it's very reasonable to expect that the weight of the Drude peak will vanish as rho minus the critical density, which gives you the insulator. On the insulator, the weight of the Drude peak should be 0. And then it tells you that the whole resistance should be varying as 1 over ρ0, rho minus ρc, which is what many people said instinctively. They said, if I have a Mott insulator, the only charge I should count are the doubly occupied sites or the empty sites, the holes or the doublons. And this formula gives you naturally this answer. Tells you that the hole should diverge as 1 over the distance in density to the transition, which will be the number of doubly occupied sites or the number of holes. So this formula has a lot of interesting features, and we are trying to test it numerically now, which is not so easy because it requires having the density dependence of these quantities and so on and so forth, and computing the Hall effect on exactly the same system to see whether there are deviations from this or whether it's really something that is exact. We tried also hard to find Laughlin-like arguments, to see if we could derive it from, but we have no gap. The system is not protected and so on, so it's not so easy. It also smells of the Streda formula that has been heavily used for the fractional or integral quantum Hall effect, but again, here we have no gap to protect the system. So I give this to your imagination, and this is something that I find as a remarkable relation between two, let's say, transport-like quantities. I would like to finish by another work that we did on triangular ladders. So all that I showed was on square ladders. But of course, if I take a triangular ladder like this, let's say 2 bosonic chains connected by this kinetic energy, now the magnetic field can lead to frustration. And so you can expect phases in this system which will be more rich than what you can get for the square ladder. And the person who did really the work on this is Catalina Lati, with a wizard of the MRG and a pretty damn good physicist. Now, I say this because he's on the job market. I really advise you to hire him aggressively. So, okay. So let me plot the phase diagram here. So at small flux, this is as a function of the ratio of the two J's. At small flux, well, you know, triangular, rectangular, Meissner phase, vortex phase, not much difference. But when you go to flux of the order of pi, then horrible things starts to happen. I won't go in detail, but I just want to tell this phase, which has a strange name. It's a biased chiral superfluid. What does it mean? It means that there is spontaneous symmetry breaking of the population from the top and the bottom. Here, there is no current forced in the system. It's just system like this, but the system spontaneously breaks the population between the top and the bottom, and in addition, it sends current on this direction and brings it back by the center. So this is a little bit strange phase. There are others that we analyzed in this paper, but the reason why I'm showing this is now, can we use the Hall effect as a probe of this phase diagram? And at least numerically, the answer is, oh, yes. If I look at the Hall effect, which is obtained by the same technique, give a kick, look at the convergence of the ratio between the current and the imbalance, you will notice that along the phase transition, both for the Meissner to vortex phase, but also for the biased chiral superfluid, the Hall effect is having very strong singularities. So the Hall effect is actually a very sensitive probe, okay, at least in the numerical study. I don't know in a realistic experiment, but it's a very sensitive probe of the existence of a phase transition in such system. And this is something that was discussed in greater detail in this paper. So I think this adds one tool, I would say, in the bag of tool of doing measurements for correlated phases, which are not so easy to identify, and at least to tell about the presence of a singularity, a presence of a phase transition. It seems that this method of measuring here, it's just the whole polarization, of measuring the polarization is a very good method to tell you in a relatively complex context where you have frustration, you have here a very finite magnetic field of the existence of a phase transition. I think I'll skip this because this would bring us too far. Too bad this was the only topological part of the talk, but you can ask me questions on it if you want. So I would like to put up the conclusions. I think there are remarkable properties of the Hall effect for interacting quantum systems. Of course, we knew this in the very large field regime already with the integer and fractional quantum Hall effect, but I want to point out that this is also true at moderate or small field. We found this universal regime which gives back 1/n for large tunneling or large interactions. This is fully confirmed in the great experiments that Leo did with cold atomic gases. We have an analytic expression for the Hall effect in a two-leg ladder to Monaga-Luttinger liquid. We also did fermionic ladder, so this formula is very robust, it's there. And we are trying to understand it better. And we could extend this type of analysis to other frustrated systems. So now we need to explore and we need to understand at a much better level this physics, because I think we get something, but I'm not sure we really understand what we get. And of course, it would be interesting to extend the number of legs. And hopefully, at some point, we should also recover the crossover to the two-dimensional system. So on this, I will stop, and I thank you for your attention.